keynote speaker is Hana Dusíková. She comes from Czechia.
Yeah.
Yeah. So I need to get used to say Czechia and not Czech Republic.
That's fine. Both are fine.
Okay, good. As I said, she is a member of the ISO C++ committee. She has made a number of contributions to the standard, and she leads a study group at the committee. And she currently works at Woven by Toyota.
Yeah.
And what else could I say? I'm just boring you.
I can start.
And you can start, sure. Thank you very much, Hana.
Okay, hi. Hi, I am this talk, but we have been waiting for. The grammar error is there intentionally. And I'm Hana. I'm working for Woven, as Daniel said. I'm also co-chairing EWG and SG7 study group in C++ committee. EWG is the design group, and SG7 is the reflection group. Actually, doesn't mean I understand that. It's because I have good card heading skills. So, and I'm also author of CTRE library, compile-time regular expressions. It's a fast template library to implement regular expressions, and also small funny library CTH, which is SHA2 and SHA3. Oh, sorry. Yeah. And implementation. Yes, and because this conference is about JavaScript, so I love JavaScript. How many of you love JavaScript? Like one. Thanks. Two. Great. How many of you try to use JavaScript? Did you like it at least? Did you hate it? Love and hate in one person, yes. Okay, why did you hate it? Note for the video insert cricket sound. So, I love JavaScript because it's really easy to make stuff done in it. And sometimes in C++ it's really hard to do stuff. For example, I did this small thing on the committee meeting a year ago, which is a search engine in JavaScript, and you can search in C++ standard for thread. Did you know there is a Jurassic Park in C++ standard? Jurassic, and if you look here, it will open, and there is Jurassic on the page. Yes, and there is also Velociraptor and other dinosaurs. You didn't know. Anyway, let's go back. So I have this search engine. It's done in JavaScript, and it doesn't load for index to your browser because it's a pig. So you need to download it, and you don't want to download it. Oh, it's moving fast. Anyway, no. So in JavaScript, when you download something, you just ask, "That's my domain." So I download my index page and put it into variable, and if it's function fetch in the URL. And if I want to download anything else, I will just do fetch pop icon. And if I want to render page, there is a function magic render, and in it I will just provide page and icon. But it will do nothing. We need to await for on it. But it will download both resources simultaneously and wait for both of them to finish. So the render will be called when both are ready, but they will be downloaded together. But you need to put it into a function which needs to be marked async. And that's the difference between C++ and JavaScript. You need to mark function async in JavaScript, and in C++ you do it a little bit differently. We will get there later. There is also a cute thing in JavaScript, promise.all. So you can have async function which will download page by provided URL, download it, await for it, and then it will parse it, get all the resources from it, like hard links, images. Then you can map the URL with fetch function, and it will return promise to the resource itself. and you will have like array of resources, and then you can take the array, transform it into one big promise, and await for all of them to download, and provide a page and all the resources as one object easily from function. So you did actually fetch page, await to do it, so browser can do something else, or JavaScript engine. Then you parse it, then fetch all the resources, and then await for all of them. Browser can do something else, and then function is finished. It's really easy. That's why I love JavaScript. Do you like it? Yeah. Why cannot we do this in C++ easily? So in C++ we have libcurl, which is like major library you can already use.
The phone is doing interference.
Okay. Sorry. Okay. In C++ we have libcurl. How many of you use the libcurl? At least once. It's really easy. It's pretty straightforward. But it's not asynchronous if you want to do it nicely. So libcurl 27-year-old. It's C API. It's not C++, and it supports almost any internet protocol. You can name it. Even in the IPFS, Interplanetary File System. You can download on Mars, and curl is used on Mars. So how do you use it? You initialized your handle. You need to check if it's null, because you need to check everything. Then you provide URL you want to download. You tell it that it can follow like redirections, and then you do perform, which will download the stuff. You will check if it's done, and otherwise it's an error, and you delete the handler. It's C, how it's done in C, so no RII. But how many of you try to like write a wrapper of libcurl? 1, 2, 3, 4, 5, 6. Okay, it's pretty straightforward. It's just RII wrapping. So we can go a little bit forward. With C++, we have like string, and we can like provide like callback, which will be written every time I need to write data. It's just like a lambda cast to pointer, and every time I get some char and size, I will just build I will like take the string, the output string, and append to it as a string view slowly as I'm downloading. It's not efficient, but it's enough like for a slide. And then I return number of like bytes written. Then I provide the function to this libcurl and perform, and now I download it into string, and otherwise I have runtime error. It's a little bit more C++ way. It's not RII yet. So let's wrap it into RII. Let's have easy handle, some constructor, some like constructor for URL, some destructor, options to set URL, to set follow location, to write into, provided as a nice callback, provided as a object to write into, and then since perform function, which will synchronously perform all the operations and get you a result as a enum. Easy. Do you follow me? Okay. So let's have function fetch in C++. We will create the handle, set that it can follow the location, provide output string. We will be writing into the string, provide start the since performation, and otherwise if there is error, throw an exception, and then finish and return the string. It's, I think, C++ 101. Mostly. So I want to do it asynchronously. So I will have like a promise type, because I'm using name promise because it's the same as in JavaScript in other languages. Python is using task. Senders receivers in C++ will use also, I think task, but I'm not sure. I'm not following that much. And there is a difference. There is a co-await keyword. How many of you are familiar with co-await keyword? Okay, like about half. I hate it because it's co_, but you need to choose battles. So co-await mean it will wait on this point and it can do something else, or it will maybe it will just do something else somewhere else, or it will jump completely different. But otherwise, the code is same as the previous. With exception, it's not since perform but perform. But otherwise, you can read it and you can probably understand it if you didn't use C++ much, if you came from JavaScript. And then coroutine, which will return the output in the coroutine. We have coroutine and we have return, and that's making me even more sad, but we'll get to it. So, why people don't use coroutines more? Shout a reason. At least some.
No support in the library.
There is no support from library. Yes? Anything else? In case you wouldn't give me any reason, I have like a few of them on slides, so there is no support in the standard library yet. We have the generator now, but that's not much coding. It's too complicated, someone says, because we have a lot of customization points. And it's new. It's C++20. It's 4 years ago. And it was put into standard on meeting, somewhere. I think in Cologne. Daniel, do you know when coroutine were put in the standard? When? I think it was Cologne meeting, but it was 2019. So, and there was a lot of talks before that, so I don't get it. Because for me, functions are just specialized coroutines. If you think about them, that just function, normal function you are used to is coroutine, kind of. So, what function has only one starting point and one point, and it can leave on multiple points, but it will never can go back. And because it's nicely scoped, you can reason about lifetime of the objects inside, because they are scope based. It looks like this. You have color, you will call function, it will return, you will call another function, you will return, call, and etc. Functions. Okay, coroutines, they have one starting point and multiple entry points. You can re-entry them. You can suspend them and resume, and they can have multiple exit points, like function. But how it behaves is defined by code in your library. And because every coroutine for different use cases can behave differently, it's really hard to standardize a task type. Because we don't know how to make it generic enough, or no one is brave enough to bring it to the library. I don't know. So generator looks like this. You will call it, and it will immediately return. And then next time you need a value from it, you will resume it. Then it will suspend, resume, and it will give you you have two parallel functions running to each other. That's like simple coroutine as generator. But coroutines are not threads. They are not different. They don't have different stack, at least in C++. And if you co-await on something, you are not blocking whole thread. Another coroutine can do something else. So you can interleave them. Threads, if they are blocking, you downloading something, you need to block whole thread and wait until kernel will wake you up. So if you are in memory constrained environment, coroutine can be better because you don't need to allocate stack. So in JavaScript, function looks like this. Function divide A by B, check if it's divided by 0. Asynchronous function looks same, but there is async keyword in front of it. Because in JavaScript, coroutines are implemented as a transformation on function, which will, instead of returning your original value, it will return promise that some value will be returned later. And the async keyword does that. Yeah. In C++, we have function on left, divide A and B, and yes, there is an error. And how many people can see it? That's for other talk. And coroutine in C++ are marked with type describing the coroutine, function int, but actually for compiler to know this is actually coroutine, there is a coroutine. That's how compiler will know. If you use coroutine, co-await, co-yield inside of the function, the compiler will know that function from inside is a coroutine. From outside, you don't need to know it's a coroutine. You are calling just function which will return some type, like the function int or something. But from inside, compiler does that, will do the transformation for you. And when you use co-await, co-yield, co-return, it will look for library type coroutine traits with return type and arguments of the function, for promise type, which will give you implement behavioral description how your coroutine works. So default coroutine traits will take the type name, arguments, and it will check the promise type inside of type name t is defined, and it will provide the promise type from inside of your type. But you can provide different promise type outside of your return type. So you can actually write coroutine for stat regex if you want, probably. I don't know. No one uses stat regex. But coroutines are like more or less in C++, they are modeled. But on a stack on the left, you have a function t, which is just handler. So it's probably just like pointer, pointing to a coroutine frame, which is the thing in middle, which will be probably somewhere on heap, maybe on stack, optimized, depends on its magic. And inside of the coroutine frame, there is a resume point, which points at a code where it will start the coroutine or resume. And also there is a promise type and all its members as you define, and coroutine frame on the bottom, which contains all the variables which can survive suspension. So if you suspend your coroutine and you have variables which are accessed across the suspension points, they will be put in coroutine frames. If you have variables which are not accessed or like visible between suspension points, they won't be there. They will be on your program stack as a normal function. And the code on the right, it's just some code somewhere else, and it's just static, and the resume point points at address somewhere. So coroutine handle, my model is like, it's like struct which contains some like pointer somewhere. I didn't put it actually there. And you have function destroy. You can destroy the frame itself. You can resume the coroutine, so it will start. You can check if it's already done with done function or explicit operator bool. You can convert. You can access the promise type itself from inside. Only if it's not a coroutine handle of the type void, which is like erased thing. And you can also construct the coroutine handle from reference to promise type. And you can also convert it into void star address. So you can actually interrupt this thing with C libraries and just void star and don't care. And same with correct from address. You can convert it back. So function type, let's start, let's build a function as a coroutine. Function of type name t, which means like return type of our function, will contain promise type. And handle type will be coroutine handle promise type, and handle will be stored inside a function, nothing else. And the function will be built with handle, and when the function, like the handle of it, will go out of scope, the handle will destroy the frame. And you can access the result and or explicitly with casting. Oh, I went back. Sorry. Okay. How does the resume of coroutine works? Let's say you have the resume point variable somewhere, and I think it's a lambda. The coroutine itself is a lambda. The frame is a kind of lambda. And at start, you will always jump into the resume point. And first resume point is state 1 as a default. So when you call coroutine, it will start here, do something, and when there is a suspension point, it will store the address of the next suspend point and return out of it. somewhere else. And next time you call it, and the resume point is set to state 2, it will start there, and it will store the next resumption point, and so on. It's like just go to, kind of. So, diagram. When you start call coroutine as a function, the transformation of the compiler will build a coroutine frame for you, and it will go into initial suspend point, which is every time always is present in C++ for coroutine, and you can decide what do you want to do. Do you want to continue? Do you want to go back to caller and leave it leave it there for later assumption, or you can jump to a different coroutine. It's up to you. You can go back to caller, go somewhere else, or just not suspend and continue. It depends on your use case. Some coroutines can be immediate, so eager, they will just go to initial suspend and it will continue immediately. Some will go back, like lazy task. Python does that. You will start task and it won't evaluate unless it's needed. Or you can have like chain of coroutines and you can jump somewhere else and do something else. And then if you went somewhere else and didn't continue, you can resume and continue later. And every coroutine can have your custom suspend point. That's like in your code, the explicitly written suspend point. And they have exactly the same options. You can go back to function which assumed you, or caller, or you can go somewhere else, or you can just continue. And if you suspend, and then you need to resume after that, and you continue. And at the end of every coroutine is a final suspend point, which is a little bit different. You can decide, you can go back to whoever resume you, or somewhere else, or you can continue, and it will mean that the coroutine frame destroys itself, and you will get go to resume or whoever resume you anyway. That's all. That's the C++ model for coroutines. You have like initial suspend, final suspend, and every time you co-await or co-yield, there is a suspend point. Co-yield is just information to co-await, but it's not part of this presentation. And another like slideware code, like pseudocode, every time you suspend on initial suspend point or any suspend point in your coroutine, it looks like this. It will ask whatever you are awaiting on, awaitable, if it's await ready. This is the point when you can decide if you want to go, you want to continue, or you want to, sorry, what's happening? If you want to continue, and if you not, you will suspend the coroutine, which means you will store the resume point to the frame, which is after the point. And based on what function await suspend returns, if it returns void, that's like on the awaitable, then you will suspend the coroutine and call function await suspend with current coroutine handle, and the awaitable can store it somewhere else, and then you will go back to caller. And if it's return bool, so the await suspend function can decide if you actually want to go back to caller or just continue. Then if it's if the result type is value is true, you will continue, and if not, you are like, oh sorry, if it's false, you continue. If it's true, you will suspend. And if it returns another coroutine handle, which is like go somewhere else, then you will call it, and you will go somewhere else, like a kind of it go to. And after you resume, your compiler will call await resume function on awaitable, and it will give you result of what you are awaiting for, like integer or any value, or maybe void, what you were waiting for. So C++ standards helps you a little. It provides suspend always, suspend never awaitables. Suspend always, return in await ready, always false, which means that it will always suspend. suspend doesn't do anything and resume doesn't do anything, but it will always suspend and it will go to a caller or on a resume point. Suspend never, awaitable, will never suspend and it will just go through. Because they are like building stones for coroutines in C++. So let's do the function. We have the function and now we have the promise type inside unwrapped. Initial suspend. When you call in C++ a function, it will just start immediately executing. So it will never suspend. We will use the suspend never. And after final suspend, I'm using here suspend always because I need to store my result value. But that's my choice. And a return object, a get return object function, which and the promise type. I'm showing the promise type, the initial suspend, final suspend. All these functions are mandated to be there because they are customization point for your coroutine. So you need to implement them because they define your behavior. You cannot not have them. For example, get return object will return the function itself when you start the coroutine. So if you start the coroutine, it will create the promise type, the frame, and it will call get return object, and it will give you the return object from the function transformed. Here I will just take my handle for my coroutine frame and wrap it into function itself to handle type on the bottom and return it. I have a slot for my result, optional, the result, and I have also slot for exception. So when someone use core return, it will call function return value. If you are returning void, it will call function return void, and you can store the value into the optional. It's not efficient, it's a slideware. And then you have unhandled exception. Whenever there is an exception inside of coroutine, imagine that the whole coroutine is wrapped into try catch, and it will store the exception into the slot, and you can do something else with the exception later. So I have the handle type, handle constructor from the handle type, destructor which will destroy the frame. You have function get, which will check if the handle is done with assert only, and then it will look if there is an exception. If there is an exception, it will retro it. As a normal function, if you call a function and there is an exception, it will just propagate. And if there is no exception, it means there should be a result, and it will give you a result, and that's done. And we actually write, we just write a function as a coroutine. Let's use it. This is actually a slide how it looks like unwrapped. So the transformation. So you call divide a by b, and it will actually return a function int with coroutine frame. I wrote it as a lambda, which will store the value a and b inside of the coroutine frame. It will call initial suspend, which will just won't suspend. It will just continue. Then there is a try, which will check if there is an exception. If you are dividing by 0, we'll throw the exception. Otherwise, call return value on the promise type itself, and then go to finish because you are done. Otherwise, there is also catch for any exception which can spill all the function. Oh, again. And then you call the unhandled exception, and at the end it will co-await on the final suspend, which will suspend because I'm storing the result inside of the coroutine frame. And if I destroy it, I cannot access it later. So let's build curl promise type. And I'm using promise type. It will be a little bit confusing, but I still choose to because I'm using same vocabulary as JavaScript here. So I want to download something and return t. So promise type from outside, there are promise of Cocorlo and promise type of C++ coroutines. It's going to be confusing, but yes. So promise, it can be built from the handle. It can be copied, but it can be moved. It can be destroyed if it wasn't moved. You can assign it. You can await on it because promise in asynchronous environment is also awaitable. So you can actually await on something you are downloading. So if my coroutine is finished and I return from something, it's done and it's ready. So it won't need to be suspended. I won't need to suspend. I can just continue in the image I showed you before. If it's not ready, it will call the await suspend, and it will tell the promise inside someone is waiting for me, and who is waiting on me. And the function will return other coroutine to run, because I cannot return whatever I was downloading yet, because I didn't download it. And when I download it, I will check if there was an exception, throw it. Otherwise, I will get the result from it. So, promise is promise type. Inside, we have a coroutine handle of type void of someone who is awaiting on my result. So if someone asks co-await on me, I'm storing handle here. When I start my coroutine with this promise type, on initial suspend, I will do one thing more than just suspend never. I will inform some scheduler somewhere that I started. Remember that. And when I finish, I have custom final suspend, which will always suspend. Won't return anything because it's final suspend point. I don't need to return anything. And then when I suspend it, I don't. The coroutine handle is actually itself, so it's not needed here. I will ask scheduler to final suspend me and select something else to do. So I'm not returning to whoever resume me or call me. I'm going somewhere else to some other coroutine and provide the awaitable. And then the promise type have the function someone is waiting on for me. So someone called co-await on the my promise. I will store it and ask scheduler to suspend me and select someone else to do, because I cannot do now anything because I need to download it and it will take a while. There is like the joke, how is it to like have like data in cache? It's like beer in hand. It's like I also like to have like data in memory. It's like having beer on table, and that's like having like data on storage is like beer in fridge, and having like data on network is like having beer on moon. It takes a while. So let's have like a lazy perform awaitable, which is like some like awaitable, which stores the reference to easy handle of Kokoro. It's never ready because whenever I ask to download something, it's not ready yet, so I need to suspend. Then I have await suspend, which will take the coroutine which is awaiting on something I'm downloading, associate the coroutine with the curl handle itself, and ask scheduler, which is somewhere else magically hidden, to do something else. And await resume will give me Kokoro result. So the magic scheduler behind the scene. If I have a coroutine, I call something, run it, and then I run into something I need to await. So I will suspend the coroutine and go back because I didn't co-await on it. So I can actually, and I will let scheduler know about the coroutine. I can call another coroutine because I didn't await on core 1. So I can call coroutine 2, run it, and then suspend. Scheduler will know about it, but I still didn't co-await on it. So I can run third coroutine, and it got blocked by something. I need to go back, scheduler will know, and now actually finally co-awaiting on coroutine 1. But it will happen. It asks scheduler to do something else. And now everything is blocked. What can I do? I need to do I/O. Finally, I need to do I/O because all the fast operation which happens in like memory are done, and I need to do the I/O on network. So I will ask schedule, complete something, please. But schedule don't know which will complete first. So maybe coroutine 2 finish first. So it will resume it, finish it, and when coroutine 2 reach the final suspend point, it will ask schedule to run something else. So schedule doesn't know. So it will complete something again. Coroutine 1 was finished. Fine. I was awaiting on it. So yes, I can continue. And I'm co-awaiting on coroutine 2. And on the await ready, it will tell me it's ready. So I don't need to suspend. So I can continue. And then I co-awaiting on coroutine 3. And it's not ready yet. So I will ask schedule to complete something. There is only one coroutine not finished yet. So it will finish it. I will get a resume and I'm done. It's kind of simple. It actually is. So what the schedule is doing? It has two variables: number of running tasks and number of blocked tasks. So if you inform inside of your initial suspend that you are starting new new coroutine, you will just increment a number of running tasks. And when you final suspend and select a coroutine and ask it to select something else, you will decrement number of running tasks and ask to do something else. And maybe someone is waiting for me, so I can actually provide possible next coroutine which should start immediately. Suspend and select next will increment number of blocked tasks and select something else without any hint to what needs to be run next. And select next function will take a possible hint. If there is the hint, we will unblock one task and we can just continue. But if there is a running task and block task is not same, so actually I can go back because someone is not waiting on me. Oh, sorry, what's happening? Yeah. So if the number of the task is not same, I will return no op coroutine, which is a coroutine which will immediately return to its caller. So it will mean you will jump out of the resume function, which means you will go back to one coroutine which calls you. So nothing imagine these coroutines, this model. It's like everything is a tree. So if not all leaves are blocked, you can actually go back and continue as in the image. And when number of running tasks and block tasks is same, it means all the coroutines are blocked. I cannot continue, so I need to complete some IO and return coroutine which is first completed, and then decrement the blocked and return completed coroutine. And the complete IO and return coroutine will get there soon. libcurl multi-API. How many of you are familiar with this API in libcurl? No? Oh, one. Tough crowd. libcurl multi-API is actually asynchronous C API, which allows you to add a handle from the easy interface into multi-handle or remove it, and then you can perform on the group. So you can actually prepare multiple downloads and then perform, and when there is no IO, you can actually poll on it until there is something to do, and you can actually read which coroutine, which handle was finished with this function, and that's all you need to make this happen. So complete IO and return coroutine is an infinite loop, which will call the perform on the group, and when something is finished, it will look into associate coroutine inside and return the coroutine handle from it. If nothing was finished, I will call poll and wait for some timeout and do it again. But something needs to be finished. Maybe it's an error, maybe it's timeout, or you actually download something, but it will finish. So it's not actually not infinite loop. So I lied. And fetch. Let's have function fetch. We'll take URL and number of attempts you want to download it, because there can be some error because you are in internet, and you will return promise with string of the content that you downloaded. The string is the output. You will have the easy handle provide. You will be writing into the string. You will follow location. You will try multiple times, and if there is still some attempt to do, or unless there is no, you will throw exception. And then you co-await on the perform, which will give you the lazy perform awaitable, which will associate this coroutine with the easy handler. And when there was an error, you need to resume with size, so you can actually resume download in middle and continue. Otherwise, if you were successful, you need to check the result code. If the result code is not 200 something, then you will throw exception. Otherwise, you will return string. And you have coroutine, which will download URL as you provided, and it can do it multiple things. So we need to actually wait for multiple coroutines if you want, like the promise all. So in C++, we take range of promises and return promise of vector of the promise results. So we will unwrap the promises into one big promise. We will look at the value type. We will look at the result type of the result promises. We will materialize all the promises, because it can be a lazy view. So we need to actually create the promise. So because we can work in ranges with like transform. So we can take URL and transform it into promises lazily. So we need to actually materialize all of them. Then create a vector with the result, reserve it. And then on each promise type, we can co-await and insert result into the output and co-return output. It's not downloading one by one, because all the promises were started with the materializing with the state ranges 2. It will start all the downloads together. We can also have like if our promise is returning optional t, so maybe it can fail nicely. So it's similar. We will take this. We need to materialize them, reserve space. But here we need to check actually if the result to go back to result. If the result is null opt, the whole promise is null opt. So we need to actually finish all the downloads, and if either of the downloads will fail, we need to like propagate the fail to all of them. So if something failed, we just have to done. So everything together. Let's have function all and download this file and this file. Wrap them into one promise type. This is like variant with tuple, so it's not just about like data structure, but also tuples. Co-await on it, unwrap it with structure binding, and what it will print. You don't know, because you need to download it. You need to co-await on it. It will print hello world. So we can take something more complex. We can fetch all. We take URL and we download the page. With CTRE, we can extract all the absolute address to like resources, transform them with fetch result function into the fetch resource function, which will take URL and give you a resource, which is just URL and its content, co-await them. And then when it's done, we co-await on it and return a whole page with all resources in C++. That's cool, man. How many of you think it's cool? And it's easy. You can actually see what's happening in the code. Where it's forking, where it's joining. It's like if you at least a little bit used to in like different models in different languages like JavaScript, it's natural. Let's go back. Remember the search engine I showed you. This is its version in C++. We will search for text and look for top 100 results, and we need to take n-grams, so we will take the text. We use function adjacent transform, which will look at running window of 3 characters, and we enumerate them. So it will we will also like remember their position 0, 1, 3. So we will get tuple position 1 and 3 characters, position 2 and 3 characters, and position 2, and so on. Then we will take all the engrams, transform them with a function fetch engram and shift. The fetch engram and shift will download all the occurrences for the engram itself across the dataset, and it's always like a pair of like document number and position. And the shift part of it, it will also shift the position itself by the position of the engram in the search text we are looking for. So if it's if we are looking for third engram, it will shift all the occurrences by minus 3 or minus 2 actually, because we are 0 indexed. And we will download all the engrams, collect on them, and we got all shards we need to download. We sort them by size from the smallest one to the largest one, and then we fold them with index intersection. We actually look for all the occurrences in same document and same position because we shift them from a position. And as we fold them, like we calculate the set intersection of like one of them, we will get actually a list of all the documents and there are like the occurrences. And then we can fold them again by the document ID, because we don't care about the position it's in document. We actually care about document and number of occurrences. So we will fold them, and then we will do partial sort for top 100 results and cut the result vector, let's say, and return result. And that's how the algorithm works in C++, and it's asynchronous, and it works in like not parallel. I don't want to say parallel, like asynchronously. So, but we have been waiting for. This is a library. You can use it. Thank you. We have time for questions. I was actually quite fast.
Time for questions.
So, do ask or?
Can you go back to slide? Can you go back to slide? Wait for all promises. I think it is like 49 or something like that.
I'm glad I put number there.
Yeah.
Was it before or?
Yeah, it is a slide where you mentioned that you need to materialize the
Yeah,
promises.
okay, that's a little bit later. Yeah, that's this one, yes.
Yeah, my question is, okay, what if I didn't materialize the promises and try to use those directly? What would happen? A crash on runtime, or?
If you don't if you don't materialize the promise type, they will the object itself will cease to exist immediately. So it will destroy the promise. So it will cancel the operation. So it will start downloading, or actually it won't start downloading anything. It will just stop, like it won't download anything because you are not collaborating on them. So they can be destroyed and they will be cancelled safely. So you need to materialize them because they all need to like exist. They all need to have slots to store their results. So you need to like materialize them.
More questions?
I don't buy it. There is a question.
Yeah, my question is just about the last example. You say the size of the shard was 3 characters, right?
Yeah. Yes.
Yeah. Why is 3 the size? Is just for the sake of the example?
Okay. You can go with 4 or 3. If you have like the shards of like 43 shards, you will get less combination. If you have 4, you will get more combinations. You will have more files, smaller ones. But I think Google is using 3 in their full text engine. In my previous employer in Avast, we had like this full text engine for like all binary files, so by the antivirus, and it was using 4 characters. But we have storage, so whatever. But it depends if you prefer more files. It can be problematic, or you want less results, because more combination will give you more unique combinations. And the algorithm, this one is not efficient enough. You can actually have metadata on each of the engrams, and you can actually choose, because they are overlapping, you can actually remove some engrams totally, you don't need them. Especially if the engram is really big, because you are calculating the intersection. You can do heuristic on the intersection done by linearly, or you can do n times log n, if there is big difference between these sets. But you want to have these sets smaller enough, but you also don't want to have all the files, because it will make the index much bigger, hard to manage.
Okay. Thanks.
Hi. Do we have any performance numbers comparing the original performance and the performance of this library using coroutines?
What's against what?
libcurl or similar code written without coroutines and code with coroutines, because I guess that at least the initial overhead of allocating the context and so on will be a bit high, right?
I mean, any library will, if you actually doing something in parallel and downloading, you will need to have context for allocated for all of them. So all libraries will have the memory somehow, and especially if you are downloading unknown number of files, you will need to allocate anyway. So it will allocate here. And nice property of this approach, because everything is actually tree, and you will never return the root coroutine, because when you return, it's actually finished. The compiler can actually inline them, so the coroutine overhead won't be that big. Only in the promise all, I have the allocation, which will be needed in any approach you will do. I didn't measure it, but as I said before, you are downloading files from internet. It will take at least few milliseconds. So any CPU bind performance is totally not needed to measure. But yeah, in some environment, this is not a great approach, especially if you are working for finance and you caring about nanoseconds. It will probably be there will be some different approaches, but they actually have special hardware, and they do the high performance stuff on the hardware itself. So I don't care. Okay, we have still time for questions.
Yes, we are ahead of time. So if you want to make questions, make them. We still don't have the coffee, so take advantage of that.
Okay, you can approach me later, and I will answer your question in person, because I know I'm also introvert. Yeah, believe me. And so yeah, we can talk later. I will be here for the whole conference. Thank you, Daniel, for inviting me. It's
Thank
a nice
you very
conference.
much. So, according to the schedule, we now have a coffee break, but it's still at least 10 minutes from now. No, don't worry.
Fast today, sorry.
Yeah. You were asynchronous. So meanwhile, I have a question for all of you, because Hana made the question, why you didn't use coroutines. So did you change your mind?
Yeah, that's a good question. You can just use the library. It's there. You can just use it. And give me a star, please.
Good. I will use it.
Yeah. Thank you.
Have you actually tried to debug the code? Because that's the problem I had in the past, trying to debug all that stuff. When it fails, it's really hard. So have you managed somehow to
That's a hard question, and
we can go to the coffee.
yeah, that's fine. I think I'm fine answering it here. I mean, yeah, it makes things hard because you don't have stack, but you have coroutines. It's obvious you don't have stack. So it depends on the error. If it's like error in processing, you can actually like mock it. Like if like you download the file and there's like maybe like parsing error, which is not like associated with coroutines at all, and then it's easy to debug. Obviously, this is a really thin layer. There is not much like things to go wrong here. I mean, obviously there is always something to go wrong because every line is a bug and they grow exponentially. So yeah, but there's only a few lines actually. I'm trying to write tests, and I'm trying to have like 100% code coverage whenever it was possible. So it doesn't happen often if you write tests properly, but I'm always, you will sometimes need to debugger. I'm using, and don't quote me, I'm also like recently started writing things in Clang, and in Clang it's really horrible to debug it. You like compiling in Clang, and then you like join debugger, and it will fork a different process, and what's happening? So yes, I'm using print for debugging. And for the it's actually the work best.
Before debugging and even before testing, I think one thing we need is a set of coding guidelines. So when should we have an appropriate set of coding guidelines and then implemented in Clang Tidy?
Yeah, I mean, one thing which scares me more than Clang is Clang Tidy, and again, don't quote me, Clang format, because Clang format is even scarier. I don't know. I mean, I look at the thing and I don't know how it works. And is there anyone who know how Clang format works internally? Yeah, because like it's not supposed to be exact, but it's also like yeah. But actually, like Clang itself is not that hard once you like look at it for quite a while. I'm currently implementing my proposal because they told me I need implementation. I don't know how. So I'm implementing context per exceptions because I want to take exceptions to context per, and it's not that hard actually when you look at it for like several days. It's unfamiliar for me, so.
Okay. So, any last-minute question?
And if it's about reflection, yes, we will get it in 2026.
Good. So,
yeah, we have. I mean, in international standard organization, bribing actually works. You know.
Sorry.
Yeah. Do you know that in C++20 you have stat string and stat vector in library as context per function? Like you can use them in context per. It cost me chocolate. That was the last slot before the deadline for features, so I bribed Marshall to have these things in standard.
Thank you.
So you can bribe people with chocolate.
Okay.
Don't quiz me. Okay, thank you.
Okay, thank you very much.